What's up, everybody? It's Dan from SageMathTutoring.com, and we have a video covering some geometry topics. Let's get right to it. So let's see. In exercises 1 through 4, classify the polygon by the number of sides. Tell whether or not it's convex or concave. Okay, so when you're classifying polygons by the number of sides, you're really going to refer to this information here, which is something, unfortunately, that you will have to memorize. So 3 sides is a triangle, 4 sides it's a quadrilateral, 5 sides is a pentagon, 6 sides is a hexagon, and sort of whatever you have to do to memorize that, you should do. Use your imagination, as much as possible. So nonetheless, we certainly have 4 sides here, 1, 2, 3, 4. So we know that we're dealing with a quadrilateral, right? And we know that it's concave. Now, there's sort of a formal way of understanding why things are concave, but in my opinion, the best way to think about it is it's concave if there's a dent in it. All right, and the dent itself might sort of look like a cave, okay, which obviously makes you think about the word concave. So the bottom line is this is a dented, it's almost as though this thing used to look like a nice little box like that, but then somebody, kicked this part. Imagine that's a boot and they're kicking it, and then the next thing you know, this part got sort of dented inward like that because somebody kicked it, and then you end up with this dent here, and that's the dent right there. So for that reason, we know that this is concave. Okay, over here we're looking at a triangle clearly because that's a 3-sided figure. There are no dents in this. There are no appearance of somebody kicking this thing and causing there to be a dent in it. So therefore we would call it the other thing, which is convex. So we're dealing with a triangle, and we know it's convex. Over here, 5-sided figure, that's a pentagon, no dents in it, so we know that that's convex as well. Convex, pentagon. And then finally over here, 1, 2, 3, 4, 5, 6. So that's a hexagon, but it does look like there's a dent right there, so we would say that is, of course, a hexagon, and it's concave. All right, so that's that one. Looking at problem number 5, find the perimeter of the polygon with the given vertices. So you're going to want to bring perhaps an XY coordinate plane to the table. And I'm going to say plotting these is a good idea. So G is at 2, 4, so that's going to be here. That's G. H is at 2, -3, so that's going to be down here. J is going to be -2, -3, so that's going to be right here. And then K is going to be -2, 4, which is right here. Now here's the good news. It's not always going to be this way probably, but this is one where you actually can get away with just counting. Let's connect everything. We'll make it look nice. Got that, and that. So you can sort of get away with just counting because they do want the perimeter, right? Now the perimeter is the length all the way around. So clearly we have what appears to be 7 units there. We have what appears to be 4 units there. We have another 7 units there, and we have another 4 units there. So you're going to have to add all those side lengths up. So that's 7 plus 4 plus 7 plus 4, that's going to be 14 plus 8. 14 plus 8 is 22. Okay, so that's that one. Looking at problem number 6 now. Problem number 6 says Q is -3, 2, so that's going to be right here. R is 1, 2, so that's going to be right here. We have 1, -2 for S. So this one's going to be a friendly one as well, it looks like. And then T is going to be -3, -2. So it's going to be right here. So once again, I'm going to say, let's go ahead and just count things up to get the perimeter. Like I said, it's not always going to be this easy. Sometimes you're going to need the distance formula. But when it's a nice, obvious sort of square or a rectangle or some figure that has only vertical and horizontal lines, I think that would either be a square or a rectangle, to be honest. Whenever you have that, you could just count the side lengths. So this is clearly 4 units. This is clearly 4 units. This is 4 units if you were to count. And this is 4 units if you were to count. So 4 plus 4 plus 4 plus 4 is really 4 times 4, which is really 16. So that's going to be the answer to that one. All right. Now I got a little fancy, but just know you could add this 4 plus 4 plus 4 plus 4, and that's going to be 16. All right. So hopefully that makes sense. Okay. So this is what I was sort of talking about, where it can get a little more challenging. So for problem number 9, there are different pieces of this that we're going to have to find, which is going to be a little bit tedious, unfortunately, but we are going to have to use the distance formula now. As a reminder, the distance formula is this whole thing, where you have, x2 minus x1, you have y2 minus y1, and that's all assuming you have a point that you're calling x1, y1, and x2, y2. So that's the case with that. Now, why do I talk about the distance formula? Well, I'm talking about the distance formula because they want the perimeter of this whole thing, which means we're going to have to find the length of this red one, right? And we're going to have to find the length of the blue one. And we're going to have to find the length of the yellow one, okay? Now, the length of the green one is going to be easy, right? But we need the length of all the other ones. And that's where we're going to need the distance formula, okay? Now, the bottom line is, in the big picture, the perimeter is going to be the result of adding the red side, right, plus the blue side, plus the yellow side, plus the green side. Okay, now that's kind of hard to see, but we're going to work with it. So I'm going to call this R for red. I'm going to call this blue, B for blue. We'll call this Y for yellow. Now the green side, though, we can find out right now. That's clearly 2 units right there. So we're going to say that's 2 units. All right. But now we have to go on this separate mission to find the length of the red side, the length of the blue side, and the length of the yellow side. And now that I'm thinking about it, rather than call it R, B, and Y, we'll be consistent here. I keep forgetting I have this tool where I can just rewrite stuff. So we have that. We have the blue side. Now, the moral of the story right now, though, is the fact that we already knew what the green side was, right? We already knew what the green side was, so we're fine there, right? We're fine with that part. But now we have to find the length of the red side. So the length of the red side would be a matter of using the distance formula, okay? And what are we going to do with the distance formula? Well, we're going to take note of this point right here, L, which is 1, 4, and this other point that's at the end point of the red side, which is -1, -2. So let's just say that we are going to, therefore, work with those points. I'll list them over here. We're looking at 1, 4, and we're looking at -1, -2. Let's call the first point x1, y1, and we'll call the second point x2, y2. So therefore, when we use the distance formula, we're looking at -1 minus 1 here. We're looking at -2 minus 4 here. And as a result, we're looking at -1 minus 1, which is -2. -2 squared is 4. plus negative 2 minus 4 is negative 6. Negative 6 squared is 36. All right, so this is going to be the square root of 40. Okay, now that's something that can simplify into something. That would be, let's see, what would that simplify into? Well, the factors of 40 are 1 and 40, 2 and 20, 4 and 10, and looks like it's 5 and 8. And the largest perfect square factor is right here. So the reality is we could split that 40 into 4 times radical 10, and that's just 2 radical 10. All right, so that's the red side right there, okay? So we are sort of piecing this together where the red side is 2 radical 10. We just found that by using the distance formula. Now, for my student who's watching, if you're wondering how I simplified that radical 40, refer to the last video that I had done on that topic, all right? So that's the red side. With regards to the blue side, right, the blue side, well, that's going to also be the distance formula, okay? That's going to also be the distance formula. And the points, however, that we're going to use are the points that are on the endpoints of the blue side. We have L, which is at 1, 4, and we have M, which is at 4, 0. So I'll just write those off to the side. We have 1, 4, and we have 4, 0. Let's call this first one x1, y1. We'll call the next one x2, y2. Now, for the record, it doesn't matter which one you call x1, y1, and it does not matter which one you call x2, y2. So, but you made a decision, we made a decision, so it's going to be x2 minus x1, which is 4 minus 1, and then you're going to have 0 minus 4. Okay, we're looking at 4 minus 1, which is really 3. 3 squared is 9. 0 minus 4, which is negative 4. Negative 4 squared is 16. So that's going to be the square root of 25, and that one's actually a lot nicer. That's a 5. Okay, so it turns out that the length of the blue side is 5. Okay, so now we got to figure out the length of the yellow side, which is this one right here. Okay, so of course that's going to be the distance formula again. So let's do the distance formula again for the yellow side. And we're looking at a huge square root symbol. Let's get the structure here. And the points are going to be the points associated with the yellow side. And if you look closely, we have the point N, which is at 2, 0, and we have the point P, which is at negative 1, negative 2. I say we write down those coordinates now. We have 2, 0. We have negative 1, negative 2. Let's call this one x1, y1. We'll call this one x2, y2. So x2 minus x1 is going to be negative 1 minus 2. Y2 minus y1 is going to be negative 2 minus 0. Looking at negative 1 minus 2, that's negative 3. Negative 3 squared is 9. Plus negative 2 minus 0 is negative 2. Negative 2 squared is 4. So that's going to be the square root of 13. That's actually as simplified as that could be. 13 only has the factors of 1 and 13, so I actually cannot simplify that any further. But nonetheless, we found the length of the yellow side. Okay, so we can go ahead and just transfer that right here. Okay, and at the end of the day, we also know we're looking at plus 2 right there. Now, that is the perimeter, believe it or not. I mean, we just found it. Remember, we were looking for the perimeter. We knew the perimeter would be a matter of adding the red side right here plus the blue side plus the green side plus the yellow side. Well, that's what we did right here, right? We knew that the green side was 2. We could just count that. We could see that right away. The mission, therefore, was to find the red side, find the length of the blue side, find the length of the yellow side. And for that, we needed the distance formula. We used the distance formula. And we came up with these numbers here that we're now going to add together. But you might be wondering, what's even going on with these numbers, though? Because, you know, these numbers are kind of crazy, right? You got radicals, you got a 2, you got a 5. Well, the bottom line is, in algebra, it is the case that you could use like a calculator to kind of figure out you could use a calculator to kind of figure out what these square roots are right here. But it's possible the teacher doesn't want that. It's possible the teacher just wants you to recognize that you can combine the 5 and the 2 because those are just definitely a 7, right? And then it's going to be 7 plus 2 radical 10 plus radical 13. And then you're actually done. That's as simplified as we could make it without using a calculator. You could add the 5 plus the 2. That gives you a 7. But you're kind of stuck with these because whenever the radicals don't match, you're not allowed to like combine them. Okay, you can't really add them. You have to kind of leave them like that. All right, so that's how you do that one. All right, problem number 13. They want us to find the area of the polygon with those vertices. Well, of course, we should be bringing out our trusty XY coordinate plane for that. W is at 0, 0. That's right here. X is at 0, comma 3. So that's right here. And Y is at negative 3, comma negative 3. Negative 3, comma negative 3, which is right here. And finally, Z is at negative 3, comma 0, which is right there. Okay. So we are looking to find the area of that, which is sort of interesting. Well, I would say that the key insight is that that's a parallelogram. Okay, that's a parallelogram. Now, let me just give a quick lesson about parallelograms. Typically, they're represented like this, where they're like tilted to the side like that. All right, this is kind of an interesting looking one. But they're typically tilted like this. And it's the case that you can think of a parallelogram as having an area that is the base times the height. That's going to be the area. All right. Now, very often, the base is going to be seen as this thing. Okay. Very often, we're going to call this part the base. And very often, we're going to call this sort of imaginary line that drops straight down, we would call that the height. But the problem is that with this one, you can't really, you could use the distance formula to find the base here, right? But you would have trouble finding the height, okay? So there's got to be another way of figuring out what the base and the height is here, or another way of seeing it. And the good news is that there is another way of seeing it, because you could also, let's say, tilt a parallelogram so that it's looking like this, like a leaning tower, okay? Where maybe before, imagine there was a tabletop, maybe before it was lying across the tabletop, but now the tabletop's like here, okay? And now you have this like leaning tower that's awkwardly kind of like that. Now, the bottom line is, the reason I say that is because you could also then see this as the base. This is the part that's like touching the ground. But then you'd have to be very careful. You'd have to see this part as the height. Okay? Or, if we want to keep it the same, as sort of similar concepts as what we did before, you can see this part as the height. Okay? In fact, I think I'll do that. I'm going to erase this part because I want to keep it consistent to what I told you before. The height is to go from the ceiling, it's the shortest distance from the ceiling through the object, and then you go down and you hit the floor. Well, we have the ceiling up here, and we go through the object, and we hit the floor at 90 degrees like that. Okay? So that's the height. So we could think of it like that. Okay? We could think of the height like that. Now, the good news is that's exactly what we can do with this one right here. Okay? We can do that exactly with that. Now, you might be wondering what the heck I'm talking about. Well, imagine we rotated it like that. Well, then this green part would be the base, and we can count that. That's 3 units. And this yellow part would be the height, and we can count that. That's 3 units. All right, so this one turns out to be relatively easy, believe it or not. You can realize that the base is 3 units and the height is 3 units. So the area of that particular parallelogram is going to be that green 3-unit base times that 3 yellow height, 3-unit yellow height. So, of course, we're looking at 9, and it's just as simple as that. All right. Now I'm going to put this back to where it was. That's what it looked like originally, right? But what we did is we imagined it was like this, and then we treated that as the base, and we treated that as the height. That's without question the smartest way to go about that one. Teacher gave you that one for a reason, for my student watching, just so you know. Your teacher wants you to have that flexibility to be able to see that parallelograms could be tilted over like that. Looking at this one, use the diagram to find the perimeter and the area of the polygon. Well, we'll start with the perimeter. Clearly, the perimeter is going to be a matter of adding this whole red side, right, plus this blue side, plus this green side, plus this yellow side, right? So that's going to be the whole perimeter. We'll worry about the area in a little bit. But the perimeter is going to be the blue side plus the other side. So I'll just do this for now because I want to keep it in the same color. 4 things. Yes. So it's going to be the blue side plus the green side plus the yellow side plus the red side. Okay, now the yellow side I can find right now because we could just count that. That's 1, 2, 3, 4. So we know that the yellow side is 4 units, so that part was easy. But unfortunately, we have to go on a mission to find these other sides. Okay, so of course we're going to start with the blue side. Blue side. We will be using the distance formula. Okay. Now we want to focus on the points that flank the blue side, or the endpoints, we could say, of the blue segment. And we'll say that that's -4, -5, 4, and 0, 3. We'll call this one x1, y1. We'll call this x2, y2. So we're clearly looking at 0 minus -5. And we're looking at 3 minus 4. That is positive 5 squared, which is 25, plus -1 squared, which is 1. So we're looking at the square root of 26. And that is as far as you can go with that. Looking at the green side now. Let's see. Looking at the green side. Not the best handwriting. Distance formula once again, right? The points in question would be 0, 3, and 4, -1. We'll call this x1, y1. We'll call this x2, y2. So we're looking at 4 minus 0. We're looking at -1 minus 3. We are looking at 4 squared, which is 16, plus another -4 squared, which is also 16. So we are looking at the square root of 32. Now, it is the case that 32 is the result of 16 times 2. So, therefore, we can call this radical 16 times radical 2. Okay. And therefore, we could say that that's 4 radical 2. Now, once again, for my student watching, I covered how to do this simplification stuff in the last video that I sent before, so just keep that in mind. So that's the green side. We know the green side is 4 radical 2, so we'll put that right here. All right, so now we have to find the red side. That's our final mission, at least for the perimeter. So we have the red side and big square root. Okay. The points in question will be this time -5, 4 and 4, -5. So we'll call that x1, y1. We'll call that x2, y2. So x2 minus x1 is 4 minus -5. Y2 minus y1 is -5 minus 4. we are then looking at 9 squared, which is 81, plus negative 9 squared, which is 81. Now, that's going to give us 162. Now, the reality is, to simplify that, we would recognize that that's really just 81 times 2, obviously. And therefore, we are looking at radical 81 times radical 2, and we're looking at 9 radical 2. So that's going to be the red side. So we're basically done finding all those side lengths, right? And we can simplify now because these can actually go together. You almost treat it like it's a 4x plus a 9x. You see how the radical 2 is the same? You could almost treat it like it's an x. So it's almost like it's 4x plus 9x. And if it was 4x plus 9x, we both know that that would be 13x. But instead of writing 13x, I'm going to write 13 radical 2. Okay? It's still going to be plus that radical 26, which is right here. And it's going to be plus 4. Now, unfortunately, there's really nothing else we can do with that. That's a plus symbol. There's really nothing else we can do because this radical 26, we're kind of stuck with that. All right, that cannot be simplified any further. So that's the perimeter there. Let's see. For the record, there's always a chance I'm making careless mistakes. I mean, obviously, I don't think so, but there's always a chance. Yeah, so that's the perimeter. So now we have to find the area of this thing. Now, I can see that it's a trapezoid, but that would require a proof, so I don't know if the teacher wants me to treat this as a trapezoid. Yeah, so what I'm going to do is instead recognize that to find the area, we would have to remember that we're dealing with a red triangle, right? We're dealing with this sort of blue-green rectangle, and we're dealing with this yellowish triangle. And hopefully my student watching recognizes that the area of the whole figure, okay, would be a matter of adding the area of the red triangle plus the area of the blue-green rectangle plus the area of the yellow triangle, okay? So that's how we're going to do it, okay? And we'll keep it somewhat color-coded here. Okay, somewhat color-coded. And that's going to be our answer. I mean, once we find the areas of those things, then we would add them all together, and then we would have our answer, right? Well, the area of any triangle is going to be 1/2 base times height. The area of any rectangle is going to be length times width, and the area of any triangle is 1/2 base times height. Okay, so I'm going to say, let's go ahead and draw some empty parentheses. Okay, kind of doing all of this at once. All right, this might be different stylistically than the way the teacher explained it, but I like this the best. So 1/2 base times height of the red triangle. Well, what is the base here? Unfortunately, we would need the distance formula for that, and we would need the distance formula for this height as well. So this base, which I'll make blue, is this part here. And that base would be a matter of using the distance formula. Now, if I use the distance formula for that, that's going to be square root of the two endpoints. So we're looking at, we'll say, -5 minus -2 squared, and then 4 minus 1 squared. Okay, so that's going to be -5 minus -2 is -5 plus 2, which is -3. -3 squared is 9. We have 4 minus 1, which is 3. 3 squared is 9, so we're looking at radical 18. Okay, now that would simplify to 3 radical 2. So this is going to be a 3 radical 2 right here. Now if we want to find the height though, we'll call that the yellow height, which is right here. Okay, well that's going to be another distance formula situation. So let's kind of work that out. That's going to be this, right? And I'll just do 0 minus negative 2, and I'll do 3 minus 1. Now that's going to turn into positive 2 squared, which is 4, plus 2 squared, which is another 4. So that's going to be radical 8. Now that's, at the end of the day, just 2 radical 2, if you were to simplify that. So that's going to go right here, 2 radical 2. Okay. Now with regards to the green rectangle, we have the base, which I will make, it's this black thing right here. Okay. And that's going to be a distance formula scenario. And the situation there would be 2 minus negative 2, and then we would have negative 3 minus 1, and that becomes 2 minus negative 2 is 4, 4 squared is 16, plus negative 3 minus 1 is negative 4 squared is 16. So that's going to become radical 32, and that's really just going to become 4 radical 2. So that is going to go right here. Okay, now here's the beautiful thing. The height of the rectangle we already found. It's the same as the height of the triangle, and that was 2 radical 2. So we could just write 2 radical 2 there. Over here, we have a base times height. Well, similarly, we have the height. The height is this part right here, this part right here, which is the same across the board of all of these. So this height is 2 radical 2. So I'll just write that in there. So 2 radical 2. It is the case, however, that we have to go on a mission, though, to find this base. Although it certainly looks like it's probably 2 radical 2. Just in case, let's use the Pythagorean, not the Pythagorean, but the distance formula to find this red base now. All right, so we're looking at, in this case, we'll make it red over here too. We're looking at 4 minus 2. We're looking at negative 5 minus negative 3. That would be 4 minus 2 is 2 squared, which is 4. 5 minus negative 3 is really, or negative 5 minus negative 3 is really negative 5 plus 3, which is negative 2. Negative 2 squared is 4. So yes, that is indeed going to be the square root of 8, which turns into 2 radical 2. So that goes right here. We'll make it red too. Okay, so that's 2 radical 2. So that is a big disgusting expression right there, but we can simplify it a little bit. So for example, this 2 down here would cancel with that 2 right there. So they would cancel each other out. There might be some other opportunities to do something similar. Over here, we'll discuss that when we get there. This 2 right here could cancel with any of the 2's really, but let's pick that one. So let's kind of see where we're at after that. We have a 3 radical 2 times another radical 2 plus a 4 radical 2 times 2 radical 2 plus a radical 2 times 2 radical 2. Now, let's just kind of get clear on something, okay? Now, I understand this can be getting confusing. For my student watching, just go line by line, pause the video, slow the video down if you have to, whatever you have to do to just make sure you understand each step along the way. I am kind of moving fast with the understanding that you could always rewind and slow things down if you have to, okay? But nonetheless, I want to address all this. Hopefully my student watching understands why these 2's canceled at least, right? But now we have this big mess here. Now, before we proceed, I do want to make it very clear that anytime you have like a radical 2 times a radical 2, there is a law of exponents that says you can call that radical 2 times 2. And then that would become, radical 4, okay, as a result of all that. And then the question is, well, what is radical 4? Well, radical 4 is just 2. All right, so for my student watching, just know radical 2 times radical 2 is really radical 2 times 2, because you could put them both under the same radical. 2 times 2 is obviously 4, so what we're really dealing with is radical 4. And it's the case that radical 4, also known as the square root of 4, is 2. So the moral of the story is anytime you see a radical 2 times a radical 2, you have a 2. And that's happening here. Radical 2 times radical 2. This radical 2 times this radical 2. And this radical 2 times this radical 2. All right? And then you have these other numbers that aren't radical 2. Right? You have the 4 and the 2. You've got this 2 right here. Right? So hopefully you understand, for my student watching, hopefully you understand that this is going to be 3 times, well, didn't we already say that radical 2 times radical 2 is just 2? So it's going to be 3 times 2 right there. And we'll deal with that when we get there. Over here we have the green 4 times the green 2. That's going to give us a green 8. And then we already discussed that radical 2 times radical 2. Well, that's really just a 2, right? And then we have over here the blue 2, which is just hanging out minding its own business, but that's going to be times, well, we already discussed that radical 2 times radical 2 is really 2. Okay? Now, according to PEMDAS, we are already adhering to PEMDAS, order of operations, that says we should be multiplying stuff before adding stuff. In a sense, we've already been adhering to that so far. We're getting closer to the moment where we're going to start adding stuff, but we're not quite there yet because we got to multiply these things, right? So 3 times 2, that's 6. So it's going to be 6 plus 8 times 2 is 16, plus 2 times 2 is 4. So that's going to be 26. Now, you got to be careful because that's the area, right? We just found the area after that very long-winded process, crazy process, actually. We found the area. You need to pay attention to whether or not the teacher cares a lot about whether or not you mention units squared, all right? But area is always in units squared. You could even do a square symbol like that. Okay, units squared. So that's the case. Perimeter, you don't need to say unit squared. You could say units or inches or miles or whatever it is. But for area, it's always going to be miles squared or inches squared or units squared. Okay, so that's that one. Moving forward. Okay. Problem number 27, analyzing relationships. We want to find the perimeter and the area of the square. Okay, so after that last one, this one is going to be beautiful. This one, at least part A, is going to be beautiful because we don't need to use the distance formula. It's really the distance formula that is the tedious thing, right? But whenever you don't have to use the distance formula, it's actually very quick, very fast, because you could just count. The perimeter is going to be a matter of adding the red side plus the blue side plus the green side plus the yellow side. It's going to be the length of all that added together. So we are looking at the red side, plus the blue side plus the green side, and my student watching probably can see where this is going. In fact, you might even be doing it in your head, which is good. Or not. Maybe you're not. Maybe you're just watching passively, which is fine too. So we have P equals the red side. Well, what is the red side? The red side is, and they do say it's a square, the red side is just 4 units long, right? So that's 4 units long. Now here's the deal. Since it's a square, we already know all of the side lengths are going to be 4, right? They're all going to be 4. So at that point, we're looking at 4 plus 4 plus 4, that's 16. Okay, that's 16. Now, we satisfied finding the perimeter, but we also want to find the area. Now the area of a square is always going to be the side length times itself, also known as side squared. Well, we already found the side length of each side. It's 4, so that's going to be 4 squared. That's going to be 16. Okay, so that's that one. We just found the area. So the perimeter is 16, and the area is 16. So very interesting, right? Very interesting. They're the same. B, connect the midpoints of the sides of the given square to make a quadrilateral. Is this quadrilateral a square? Explain your reasoning. Okay, so the midpoints are here and here and here and there, right? And we're forming a new quadrilateral, and that quadrilateral is this. Okay. And they want to know, is this quadrilateral also a square? Well, you know it's a square if all 4 side lengths are equal. Okay. And also if you know that there's 90 degrees at the corners there. Okay. Now, how would you know if all 4 side lengths are equal? Well, unfortunately, you would have to use the distance formula. So this is right here. This point appears to be -2, 0. This point appears to be 0, 2. This point appears to be 2, 0. And this point appears to be 0, -2. So you would have to find the lengths of the blue side, the green side, the yellow side, and the black side in order to confirm that the side lengths are the same. Now, it certainly looks like they're the same, but nonetheless, here's the distance formula. So for the blue side, we are looking at, looks like that would be 0 minus -2 and 2 minus 0. So that's going to be the square root of +2 squared, which is 4, plus another +2 squared, which is 4. And that's going to be a radical 8, also known as 2 radical 2. The green side, if we were to do the distance formula for that, that would be 2 minus 0. We would have a 0 minus 2. And we're looking at a 2 squared, which is 4, plus another -2 squared, which is 4. So that's a radical 8, also known as 2 radical 2. The yellow side distance formula would be, that appears to be 2 minus 0 squared, 0 minus -2 squared. And that's going to be 4 plus +2 squared, which is 4, and that's going to be radical 8, aka 2 radical 2. So that checks out, and then we have the black one, right? So we have the black side, which is going to be a distance formula situation, and we're looking at 0 minus -2, and we're looking at -2 minus 0. And that would be a +2 squared, which is 4, plus a -2 squared, which is 4. And that gives you a radical 8, also known as 2 radical 2. So all 4 sides are indeed equal. Now, that seems like it should be a square. The problem is, though, in order for something to be a square, not only do all 4 sides need to be equal, but it needs to be the case that there's 90 degrees at the corners. So we would need to verify that as well. And you know that you have 90 degrees at the corners if this side is perpendicular to that side. Okay? We could say we know there's a 90 degree at this corner if this side is perpendicular to that side. We know there's 90 degrees at this corner if this side is perpendicular to that side. Now, perpendicular lines have opposite reciprocal slopes. So what we could do is we could go on a mission to find the slope of all of these, All right, find the slope of the blue line, find the slope of the green, yellow, and black line. Now the slope formula for the record is y2 minus y1 all over x2 minus x1. If we were to find the slope of the blue line, that would be, it looks like it would be 2 minus 0 all over 0 minus negative 2. And that gives us a 2 over a positive 2, also known as 1. All right, that's the slope of the blue line. For my student watching, once again, slow it down if you have to, rewind if you have to. The slope of the green line would be 0 minus 2 up top, and then 2 minus 0 down below. So we're looking at negative 2 over positive 2, also known as negative 1. The slope of the yellow line is going to be, looks like that would be 0 minus negative 2 up top, and 2 minus 0 down below. And that's going to become a positive 2 over a positive 2, which is a 1. And then finally, the slope of the black line would be a, let's just say 0 minus negative 2 up top, and a negative 2 minus 0 down below. So that's a positive 2 up top, a negative 2 down below. Next thing you know, you have a negative 1 here. Now, the bottom line is these are two adjacent sides, like the blue side and the green side are next to each other, right? Here's the blue side, here's the green side. They're right next to each other. So are the slopes opposite reciprocals? Well, yes. 1 and negative 1 are opposite reciprocals. And the way that I know that is because there's secretly a little 1 underneath there. And there's a 1 here. So you could think of it as this thing right here getting flipped upside down and then turning into a negative. So if we were to flip that upside down, in other words, turn it into the reciprocal, well, it would look like this, right? It would look like that. And if we made it the negative reciprocal, we would just put a negative in front of it. And that's just negative 1 over 1, which is just negative 1. So that's why negative 1 is the opposite reciprocal of 1, okay? So to make it very clear, the opposite reciprocal of 1 is negative 1. So these are two adjacent sides which are opposite reciprocals of each other, and that does indeed mean that there's 90 degrees at the corner here. So we've established that that's 90 degrees because these are perpendicular. How do we know they're perpendicular? Because the slopes are opposite reciprocals. We just established that here. Now we have the green side and the yellow side. These are also adjacent. So the question is that 90 degrees right there? Well, let's compare the slopes of the green side and the yellow side. Are they opposite reciprocals? Yes, they are. So therefore we know that the green and the yellow side are perpendicular, and therefore 90 degrees are there. Another pair of adjacent sides are the yellow and black sides. So the question is there 90 degrees there? Well, I don't know. Let's take a look at the slopes of the yellow and black side. The slope of the yellow side is 1. The slope of the black side is negative 1. Are they opposite reciprocals? Yes, they are. So therefore, that's a 90 degree angle right there. These are perpendicular. And finally, the black side and the blue side are also adjacent. So that's these two right here. Do they have opposite reciprocal slopes? Well, yes, there's a positive 1 and a negative 1. So it is the case that this is also going to be 90 degrees. Now, this is the way to formally sort of demonstrate that this is indeed a square. It's possible the teacher is allowing you guys to just sort of eyeball it or something. I would be surprised by that, but I understand that this seems like a lot of work for such a little thing, but in my experience with math, you do actually have to be very thorough. You can't just make assumptions. And the bottom line is, they're asking if this thing is a square. We don't know if it's a square unless the side lengths are equal, which we did verify through the distance formula. But we also don't know if it's a square until we have verified that there's 90 degrees at the corners as well. And the only way to do that is to analyze the slopes of the adjacent sides and find out if they're perpendicular to each other. So that's that. Part C, find the perimeter and the area of the quadrilateral you made in part B. Okay. Yeah, so of course I lost all of my information, but the good news is I do remember what the side lengths were. before, when we found the side lengths, we had established that the side lengths of that sort of diamond square are 2 radical 2. I don't know if you remember that from my student watching, but we had already established that the side lengths are 2 radical 2. Okay? And if we want to get the perimeter, well, the perimeter is going to be a matter of adding all of that. So that's 2 radical 2 plus 2 radical 2 plus 2 radical 2 plus 2 radical 2, right? And that's going to ultimately be, remember how I said that you can almost treat this like 2x plus 2x plus 2x plus 2x, and therefore if you were to add all that, it would be 8x, but in this case it's 8 radical 2. So that's the perimeter. They also want to know the area of the new quadrilateral. Well, the area is going to be length times width, or side squared, I should say. So the area is going to be side squared, so that's just going to be 2 radical 2 squared. Now in reality, that's 2 times radical 2 times another 2 times radical 2. We already established that anytime we see radical 2 times radical 2, that's just going to be a 2. We had already discussed that. And we also have these blue 2's. So the reality is that in this case, the blue 2's are going to multiply to 4, and then the radical 2 times radical 2, as we had already discussed before, that's just going to be a 2. So that's going to be 8. So that's the area of the smaller square, right? Now, they want us to compare this area of 8 to the area of the square we found in part A. Okay? Well, the area of the square we found in part A, the area of the original square, which is the big square, was 16. So they're just expecting us to note that the area of the big original square is 16, the area of the smaller square that we created is 8, and 8 is clearly half of 16. So I think what the teacher is getting at here is anytime you draw these midpoints on the original square, and then you consider the new square that you just formed by those midpoints, you're going to end up with a square that is literally half the area of the original larger square. And that will happen all the time. It doesn't matter how big this original square is. If you hit it with midpoints on each side and connect the dots, form a smaller square inside the larger square, it will always be the case that the smaller square will have half the area. Now, once again, be careful. Maybe your teacher wants units squared. Maybe your teacher wants units squared. Anyway, hopefully that's helpful for my student watching. Yeah, actually pretty extensive homework assignment, I will say. So that's a lot of information. It does appear that you already have your work cut out for you this semester. So you must pay as close attention to everything. You must not miss a single thing the teacher says, because this teacher is moving rather quickly. All right, so for those of you watching, other than my student, good luck to you as well. Hopefully this was helpful, and I will talk to you later. Bye.